Okay, so let me start by thanking the organizers for giving me the opportunity to talk here. And so today I'm going to talk about survival probability and record statistics for random walks. And so this is a project that I've started at my time when I was in Weizmann, but I've moved since to King's College, and it's in collaboration with Francesco Mori that you heard yesterday. So so this is the plan of my talk. So first I'm going to do a rather simple introduction into the concept of generally extreme value statistics and record statistics for different kind of systems. Then I'm going to recall some properties of these kind of statistics for continuous symmetric random walks. And then I'm going to present the model that we consider in our paper, which is a model of random walk where the step where the sign of the steps are correlated. Okay, so let me first mention briefly some introduction about extreme value and record statistics. So I think I don't need to mention that much that extreme value statistics are important. I mean, I'm sure you are all convinced of it, but just for the sake of the argument, let me mention that they are extremely important in climate science, especially nowadays, in finance, in sports, and as we have seen also recently in epidemiology. And it is then quite important to have a good understanding of their occurrence and have good control on simple model system to understand how the statistics works. So first, let me mention a few definitions. So consider this time series here. One can be first interested in for example, simply the maximal value that is reached in a given time step n, and one can be interested as well as the time where it occurs. So these are simple enough statistics, but then if one wants to have some refinement, one can also consider how it evolves with time. So you have different records, for example. So the first record is attained at the first step, and then at the second step, and then you have to wait for some time before you hit another record. And so you can consider, for example, simply the number of records in a given interval. You can also consider the values of the different records and the time at which they occur. So the simplest hypothesis that one can do to model this kind of system is to consider ID random variable. And for this kind of problems, of course, the statistics of extreme value and record are extremely well known. So first, for the case of extreme value statistic, the probability that the maximum is reached at step k is simply uniform in that case. And as is well known, the cumulative probability of the maximum value can be obtained rather simply as the product of the cumulative probability for each individual variable, and it's given by this formula. And in the large n limit, it's well known that the typical value is given by either a Gumbel, a Fréchet, or a Weibull law, and this is known as the Fischer-Tippett-Gnedenko theorem. Now, the statistics of records can be also obtained. I mean, this is a bit less well known maybe, but this can be computed quite simply. by introducing, for example, this random variable, alpha k, which is an indicator function. It's given by 1 if xk is a record, and by 0 if xk is not a record. It turns out that these variables are independent of each other, and the statistics can be computed rather simply. So imagine that you want the probability that the kth value is a record. You just have to compute the probability that the k minus 1 value are less than x, and then put the weights associated to the probability that you have a given value x. And as you can see, this integral turns out not to depend at all on the parent distribution P of x, and you just obtain this simple answer that is given by 1 over k. Okay. And from that, you can compute the joint probability that a record, the ages of the record are L1, Lm. Just to recall, the ages of the record correspond to the time during which a given record is holding. And so it's given by this simple formula. And you also have the probability that there are m records. And so in this simple case, all of these statistics are completely universal. They don't depend on the parent distribution P of x. And you can compute the average value of the kth age of the record, and you obtain that it grows logarithmically. I mean, there is this log of n that is appearing, and it grows with k as well, which you can understand rather simply because to obtain a record after a number of records have been obtained, you need to have an extremely large values. And because of all of these values are IID, you need to wait a long time to reach this extremely large value. And so you can compute the full probability that there are a number m of record, and it's given by this simple Gaussian scaling function in the large n limit. Okay. So these are the record statistics for IID. So far, it's very simple. Now, let me mention briefly also survival probability that will play a large role in the statistics for random walks. So survival probability is an object that has a long history in stochastic processes. And so generally, given a stochastic process, x, you can compute it, so if it's discrete just that way, supposing that at any given step, the stochastic process remains positive, given that it started from a positive position. And if it's time continuous, it's often called persistence probability, and it's given by something similar. So it has been the focus of a lot of different works, and you can see some review about this in these two papers. And it's extremely important in all of the searches process, because from this survival probability, you can define a first passage probability, which is just given by the time difference of the survival probability or the derivative in continuous time. And you can judge, for example, the efficiency of a search process by considering the mean first passage time that is just given by the average value of this object with respect to n here or with respect to t here. And again, this has been the focus of many research for a long time. And it has many applications in different parts of science in general, so both in biology and chemistry, when you think about a reactant that is searching for a given reactive site, for example. And in computer science, when there is an algorithm that is searching for some given value, so you have this search process. And in the last 10 years, there has been huge activity on this precise subject in the context of stochastic resetting. And it was found that if you use this kind of stochastic resetting, you can expedite or render finite the mean first passage time, even in cases where it was infinite for the simple process without resetting. Okay, so this was concerning the survival probability, and we'll see that for random walks, these two different objects, the survival probability and the extreme value and record statistics are quite linked. So for a continuous symmetric random walk, you just have this recursion relation, right? I mean, xi plus 1 is xi plus eta I. And we consider the increments to be continuous IID and symmetric. So you have this distribution P of eta for the increments. And as Francesco mentioned yesterday, there is this well-known Sparre-Andersen theorem that gives you the probability that given that you start at position 0, all of the position will be, it should be larger or equal to 0. And it's given by this formula here. And so from this expression, you can obtain rather easily in the large n process that the survival probability vanishes as 1 over square root of n. And in 1D, indeed, you can check that in this process, the mean first passage time is infinite. Now, you can use also this survival probability to obtain some statistics of extreme value. And a simple way to do that is through path decomposition. So you see that here you have a given random walk that starts at position 0, and it reaches its maximum at step 2, and then it continues. And so you can define the two subwalks that are given by this one. So you start from this position, and you do the inverse steps. So here you would go up and a bit up again. You can see, so this would be the mirror image of this walk, and it's given by this. And now you can consider also the independent random walk, which is given by what happens for steps that are larger than this value. And so you again start from 0 and you remain positive for a number of steps that is 8 in that case. So you can decompose your path in this way, and you can obtain that the probability that you reach the maximum of the walk at step k is given by the survival probability for k steps multiplied by the survival probability for n minus k steps. And in the large n limits and k over n of order 1, you recover the celebrated arcsine law for the distribution. So you can see that this path decomposition is actually quite nice to obtain a simple probability. Similarly, for the value of the maximum, you can obtain the value of the maximum through the survival probability, but now starting from a positive position. So consider again this random walk. You see that this random walk is always less or equal than the orange line here. And so you can define an alternative random walk that starts from this, blue line, and that stays positive. And that would be equivalent to this one. And you can see that now the probability that this random walk stays below x at all time is equivalent to the survival probability for this new random walk. Okay. And so you can obtain again that this probability of the maximum starting from 0 that you stay below x is equivalent to the probability that starting from x, you stay above 0. Just because the steps are symmetric in that case. And so in the large n limit, you can, this object is not universal, but in the large n limit, you recover the diffusive scaling and you obtain that it's simply given by this half Gaussian law. Okay. Let me just mention that one can go beyond that and consider order and gap statistics. So if one is not just interested by the value of the maximum, one can compute, for example, the second maximum value, the third maximum value, and this is known as order statistics. And one can also consider the gap statistics, so that is the difference between two values of the maximum. So for example, the first gap would be the difference between the global maximum and the second maximum. So it's the statistics of the kth maximum, yeah. Right? Okay, and so there has been some works on this order and gap statistics recently. At the Orsay lab. Now, finally, let me mention how to go from this survival probability to the record statistics. So again, you can do that using a path decomposition. And you see that now when you reach a new record, it corresponds to the first time that you go above the preceding record. So you can again decompose your walk into different subwalks. And for each subwalk, you have independence. And the probability that you break a record will be given by the first passage probability, simply in that case. And the last record is a bit different because it's just that you haven't broken it until you reach the last step. So it's just given by the survival probability. And so this joint probability of the number of records and ages was derived for the first time in this PRL of 2008 by Satyam and Ziv. And now from this object, you can compute again, for example, the average value of the age of the record. And you see that it doesn't really depend on K and that it grows like square root of n. You can as well compute the number of record, and you obtain in this case that in the large n limit, it is again given by this half Gaussian law. And contrarily to the case of IID, it's not peaked around its mean. Okay. So that's pretty much what is going on for the usual random walk, and there are all kinds of refinements that one can consider. One can consider random walk in discrete space, continuous time random walk, multiple random walk with a drift. You can consider a random walk when you have non-zero probability to stay at the same position. You can add resetting, you can consider integrated random walk. I mean, there are all kinds of things that you can do. Okay. So you can look, for example, at the statistics of the increment. So each time you break a record, you can look at by how much do you break it, for example. Yeah. Mm-hmm. I know that there is recently an article on planar random walk. So you consider, for example, in 2D, and you can consider the random walk where you go for the first time beyond the value that you have gone in a given sphere. But the problem is that for this kind of random walk, you don't have the nice property that you have in 1D, that for each random walk you have the same thing as the one before. This renewal property, you don't have it for planar random walk. Okay. So let me now introduce the model that we considered in our article, which is given by this. So now we decompose the new step by its sign. So sigma will be the sigmas will be plus or minus 1, and eta is just a length now. So it's always positive, and it has a continuous distribution P of eta. And now we suppose that this sigma I will be, so sigma I plus 1 will be the same as sigma I with probability Q, and it will be opposite with probability 1 minus Q. So this Q parameter will fix some type of persistence in the random walk. Okay. Kind of. And we'll see that indeed there are some relations to RTP, namely. So first, some special cases. So in the case Q equal 1/2, you just recover the usual random walk because the sign of the step doesn't really matter. For Q equals 0, you see that at each time step, you change your direction. So this would correspond to an alternate random walk. And in fact, you can map this model to the local extrema of a trajectory of RTP particle. So you see that here you have this trajectory of RTP particle. And now you consider just the extremal points here, which are given here. And this would correspond to the alternate random walk that I mentioned. Okay? But now the difference is that here you have continuous time, and now I consider just time steps that are the same. Okay. Okay, so that's for Q equals 0. And for Q equal 1, the walk is unidirectional, so that's not very interesting, but there is a persistent scaling regime that corresponds to the limit where both n goes to infinity and q goes to 1, with n 1 minus q, which is given by a value of order 1. And then you can compute the probability that for some kth number of steps, you stay in the same direction, and it's given by this nice exponential formula. So again, you recover some kind of RTP trajectory, but now in continuous time that is just given by tau is equal to k divided by n. Okay. So let me first go to the main result, and then I'll explain a bit how we derived them. For this model, you can compute the survival probability Sn plus or minus x0, that depends on q, which is the probability that x1, xn are all positive, given that you started from position x0 with a direction of the first step that is plus or minus. This will be the plus and minus that correspond here, will correspond to the initial direction. Okay? So, I mean, trivially, if you start with a step that is negative, you can survive, and you start from 0, you can survive just 0 step. And if you start with a number of steps that is positive, it's given by this formula. And it turns out that just like in the Sparre-Andersen case, this formula does not depend at all on the distribution of the step length, P of eta. It depends quite explicitly on the persistence parameter Q. And so you can test numerically for any value of n with different type of distribution. You see that it does depend on Q, but it does not depend on the parent distribution. Okay. Now, again, in the case where Q is strictly between 0 and 1, and you take the limit n goes to infinity, it vanishes again with this exponent 1 over square root of n. And you can consider as well the persistent scaling regime. So n to infinity, q to 1 with n1 minus q for the 1. And you can recover that this probability converges to the probability for the RTP, which is given by this formula. So that's the formula that Francesco, derived in a more general setting in these different articles. So the scaling function is the survival probability for RTP in this persistent scaling regime. Okay. Now again, you can use this formula to compute extreme value statistics. So the first thing that one can compute is the time of the maximum. So you consider the case that the maximum is reached at the position k, which is strictly between 0 and n. One can check that because xk is the maximum of the x's, this means that on the step that is just before, you need to do a positive step. And on the step that is just after, you need to have a negative step. So this you must have. And in the case where you start with a first step that is positive or negative with equal probability 1/2, you can also check that the probability that any step is equal to plus or minus 1 is again equal to 1/2. And in fact, in that case, the probability of a given trajectory of the sigma is the same as the probability of the reversed trajectories of the sigma. So now you can decompose your random walk into the two, again, same sub-walks, yj and zl, for k step and n minus k step. These two walks start from 0, and they must remain positive in order for the k step to be the maximum. And so you can just compute the probability for the k step to be the maximum by combining all these terms. So the probability that sigma k is equal to -1, the probability that sigma k is equal to minus sigma k minus 1. So just after you have reached the maximum, you must go down, and before you must go up, and times the survival probability for this object. So and then because these are universal, you recover the same kind of universality. Now the probability that the maximum is reached at the 0th step is just the survival probability, and times a factor 1/2, which is given by the probability that you start with a positive step or negative. Okay, and you can check that again, all of this is universal. In the large n limits for q between 0 and 1, you can recover the survival probability that is given by this arcsine law. And again, in the persistent scaling regime, you can consider this probability of k, of Tmax, and you can recover the distribution of Tmax for the RTP that was derived in this article. Okay. So again, Yeah, this is because of these objects, basically. In the large n limit, they don't have exactly the same scaling, so this will give you the delta function. Okay. Now, you can play the same game for the record statistics. And so suppose that now there are a number of records that is given by M, and we want to compute the ages of the record L1, Lm as well. So again, one can introduce a path decomposition. You consider in each run here that you start from 0 and you reverse this walk. So you need to stay positive for Li minus 1 step, and then at the last step, you break the record, so you go below 0. So that is again given by a first passage probability. But now you have to take into account the sigmas as well. And again, each time you break a record, you must have a positive step before. And so this will give you some additional probability to take into account. But it's not very complicated to obtain. So for the first step, you have something that is a bit different because you start with a probability 1/2 to go up or to go down. So you have this object here. Now, when you break a record, so that's for the k, which is between 2 and, sorry, this should be m minus 1. You just have this survival probability, this first passage probability. And now for the last step, you just don't break that record, so it's given by this survival probability. So in the end, you can obtain the joint probability of the number of records and their ages, and it's given by this formula. So it looks again very much like the case for Q equal 1/2, where you recover the normal random walk, but it's a bit different, and it depends explicitly on Q. But again, it's completely independent of the distribution of the step length. And now you can compute, for example, the number of records, what happens to the statistics in the large n limit. It turns out that if you want just in this case, so Q strictly between 0 and 1 and n goes to infinity, you recover this half Gaussian distribution, but you have an effective number of steps that depends explicitly on this parameter Q. And in the persistent scaling regime, you obtain a completely different object, and you can check again that it's given by this formula. So here I did not put the formula, but it's fairly explicit. It's just a bit ugly. Okay. Now let me mention a bit the proof for the survival probability, which is at the basis of all this derivation. So the first simple case is to consider the alternate random walk, where at each step you change the sign of the step. Okay. Now you see that if you start from a first step that is negative, you just survive for 0 step. If you start with a first step that is positive, then all even steps will be positive as well. Okay? Because at each time step, at all the even values, the step will be forward and not backward. So you always have that x2k plus 1 is larger than x2k. Okay. So the first step is larger than the 0th step. The third step is larger than the second step. And so the probability that all of these values are positive is just the probability that all of the even values are positive. Okay. And now you can consider a random walk zk, which is the value at all the even values. And so now you need to add two steps, one which is positive and one which is negative. And the distribution associated to these two steps turns out to be given simply in terms of the initial distribution. And it's just it's two-sided and also symmetric. So for this random walk, you can compute its survival probability, and it's just given by the Sparre-Andersen formula. So you can compute the probability that you survive for 2p steps as the survival probability for this symmetric random walk to survive p step, and it's given by the Sparre-Andersen formula. So in the end, it's not a very complicated computation in that case. Now, if you consider the case where q is larger than 0, it turns out that you can also obtain something simple in that case, just by considering the different runs of your random walk where you stay in the same direction. So let me draw a picture maybe. So consider a random walk where you start from 0. So in this random walk, there are 3 different runs. So in that first run, you go forward for 1, 2, 3, 4 steps. Now you go backward for 1 step, and now you go forward for 1 step, and again backward for 2 steps. So that would correspond to the runs associated to this step. Sorry? You said there were 3. Yeah, there are 4, sorry. Okay. And now you can consider the distribution of the number of steps in each of these runs. So that would be the tau i's, and the displacements associated to each of these steps. So in that case, you have a first tau 1, tau 2, tau 3, tau 4, and the displacement would correspond to this value, so y4, here you have y3, and here y1, y2. Okay. Now we take those to be positive. Okay. And you can compute simply the probability that your run lasts for tau I for a time tau, which is just given by q to the tau minus 1, because you stay in the same direction for tau minus 1 steps, and then at the final step you go down. So it's 1 minus q, q tau minus 1. Now for the last step, for the last run, it's just that you come to the end of your final time. It's not that you switch direction, right? I mean, this for this particular one, it's just that I run out of time. It's not that I change direction at the last step. Okay. So the weight is a bit different. It's just given by q to the tau minus 1. And you can also compute the distribution of the displacement in each step, so which is just the sum of the eta associated to each run, and which is given by this simple formula. It turns out that this distribution will not be very important in what we just take into account that this distribution is normalized. Okay, so now suppose that the walker changes direction r times, and we define these different runs. And so if we can compute the joint probability associated to the times of this run and the displacement of these different runs, which is given by this simple formula. So for each run, you have f of tau, which is the probability that you stay in the same direction for tau step, and p tau of y is the probability that given that you stay in the same direction for tau step, your displacement is y. Sorry. Okay. Now, the survival probability, you can compute it explicitly given this joint distribution, and it's given by this formula. So you sum over all the possible number of runs, so which are 1 up to n. You sum over all the different times of each run, given that their sum is equal to n, and you integrate the dy's with this particular weight, which is that for the first run, you must have that y1 is positive. Then the second run, you go down, so it's y1 minus y2. So let me show you. So here you go up for y1 steps. Now you go down for y2 steps. Now you go up again for, you go up again and the difference is y3, and then you go down again and the difference is y4. So you see that if all these points are above 0, then the walk itself remains above 0. And so that's how you can understand this formula. And if you take the Laplace transform, you can obtain this this explicit formula where now this distribution p tilde of s depends on the Laplace parameter s, but it's normalized. Okay? And now you can again define this random walk zi. Well, zi plus 1 is zi plus minus 1 to the I, so each time you change, and the displacement now is given by this yi. Okay? And if you give to this yi the continuous distribution p tilde of s, then you recover that this probability here is nothing but the probability that starting from 0, you have survived for an alternate random walk. Okay? So you can, so now that you know the probability for the alternate random walk, you can consider the case for any value of q just by plugging in this value, and you obtain that the survival probability with any parameter q is given in Laplace domain by this. Okay. And then when you invert this generating function, you obtain explicitly the formula. Okay? Now, let me just mention briefly survival probability for when you start from a finite position. In that case, you don't have the same universality, but you can write a recursion relation for the survival probability. So the survival probability for n step is given by the probability that on the first step you make a positive. So this is the survival probability that you survive for n step given a first positive step and starting from position x0. So you consider what happens during the first step. So after the first step, you arrive at the position x. this position for the walk to survive must be positive, and you have an associated displacement, which is just given by x minus x0. And now you can consider that on the next step after the first one, you will have also a step that is positive with probability q, and a step that is negative with probability y minus q. Now, if you start with a negative step, this will be inverted, so it will be a negative step with probability q and a positive step with probability 1 minus q. And you just have to change the boundaries of this integral here. Just for the displacement for the walk to survive, I mean, you have to adjust the boundaries. Okay. Now, from this recursion equation, you can obtain the recursion equation for the. You can obtain an explicit equation, integral equation, for the generating function, which is given by this formula. And in general, it's very hard to solve for any for general distribution P of theta. But it turns out that in the exponential case, P of theta is equal A exponential minus A eta. When you take the derivative respect to eta, you obtain the same distribution up to a factor. And you can solve explicitly this recursion by taking a derivative on both sides. You obtain an explicit differential equation from the integral equation. And now you can obtain from this explicit expression for S starting from any given position x0 in the Laplace domain. And again, you can obtain, for example, the large n limit, and you can recover that in the large n limit, in this normal limit, you obtain the survival probability for a normal random walk with an effective number of steps that is given again by this formula. And in the persistent regime, you can also recover the survival probability for the RTP. Okay. So now let me conclude. So we have considered a simple Markovian generalization of the random walk with steps of correlated sign, and we have obtained explicit exact result for survival probability and record statistics. And all of these are completely universal with respect to the step distribution. And this model can be linked to the model of run-and-tumble particles, and we have derived the record statistics for this model for the first time. And with this, I thank you.